Okay, so in this section of the non-equilibrium thermodynamics, we've been talking about redox reactions, and we looked at batteries and so on. Now we're going to shift gears and talk about transport, so material transport or other kinds of properties. Whenever there's a gradient, there's a flux vector. And so whenever you have, like just think of a pile of dirt, you pile it up, and the more you try to make that dirt pile steeper, the more likely it is that the dirt's going to roll back downhill. So the steepness of the pile is the gradient, and then the dirt or sand rolling downhill is the flux. Okay, and it starts with this kinetic theory of gases, so how particles move in nature. And so this is sort of the foundational piece to all of those other flux coefficients. Some of the flux coefficients you've heard of, like diffusion. You've heard of diffusion. You've heard of ionic conductivity. Viscosity is a flux vector also, and thermal conductivity, so how heat flows through objects. And all of that is resting on this theory of the kinetic theory of gases. So it's surprisingly easy because we can just treat these gas particles as billiard balls, in 3 dimensions. So even though we have sort of quantized energies, in terms of their properties and how they move around, we can use that equipartition theorem for translational motion and set that equal to the kinetic energy of a particle. And so we have 1/2 mv squared is equal to 3/2 RT, and you realize that 3/2 RT is just the translational motion. Okay, and so this is, then this means that as you raise the temperature, the velocity of the gas goes up. That's the square root of temperature dependence. Okay, and so we know that. I mean, if you have a hot gas, you've got more kinetic energy than a cold gas, and the kinetic energy equation is 1/2 mv squared. So pretty straightforward. Now we get into measurements of these velocities. There's different ways to do that. And one of the ways is to measure the effusion of a gas. Now this is a picture of effusion where you have all of this gas trapped in one side of the container and a pinhole that lets it leak out. And so gas leaks are effusion. And so if you have a particular leak, the effusion rate is going to be proportional to that root mean squared velocity, the RMS velocity.
Professor, did you say gas leaks are effusion?
Yeah, gas leaks are effusion. Mm-hmm. What's interesting too is if there are intermolecular attractions, so this is all using, I guess, an ideal gas theory, but if there are intermolecular attractions, then the gas that leaks out will cool down because you have to break those intermolecular attractions that it's experiencing in the more dense gas. You have to break those apart. That's that Joule-Thomson coefficient that we talked about, weeks and weeks ago. And so there'll be some bit of cooling. And you can think of that as if it's cooling, it's slowing down. Well, think about this gas is leaking out through that pinhole, and it's attracted to the gases behind it. And so it loses a little bit of its velocity, which means it's cooler. Okay. Now the units are a little bit interesting. I went ahead and created this capital M, just to sort of indicate this is the molar mass, and it's in kilograms per mole, okay? Because the kilogram is needed for the joule. So inside that joule is a kilogram meter squared per second squared. And so you see that here. This is the velocity squared, that's the meters per second squared, and then you need a kilogram in the mass to give you joules, and it's kilograms per mole is compatible then with this joules per mole here. Now, diffusion is different. Diffusion is the spread of one substance throughout a second substance. And so we'll talk about diffusion. Let's see, today's Wednesday. I think it's I think it's Friday. Friday's diffusion. So we'll get into diffusion on Friday. Friday we cover thermal conductivity and diffusion, and then Monday we talk about flow. So viscosity and flow through a pipe. Now, the homework that's due this Saturday has Monday material in it. Okay, specifically Poiseuille's law. So you find at the end of that those notes, Poiseuille's law, that's the single equation you need to use to calculate all of the different flow questions in that homework. So just look ahead to Monday's notes when you're doing the homework, and you can figure it out because there's a flow rate in like liters per minute. So volume over time, that's the flow rate. And it depends upon the radius to the fourth power, or the viscosity, inverse of viscosity, or the change in pressure, or the length of the pipe. And so I ask you a bunch of questions. If you double the length of the pipe, what happens to the flow rate? Okay, well, it would be cut in half. If you double the viscosity, what would happen to the flow rate? Well, it's inversely proportional to the viscosity, so it would be cut in half. If you double the radius of the pipe, what happens to the flow rate? Well, it's radius to the fourth power. Okay, so 2 times 2 is 4, times 2 is 8, times 2 is 16. So just doubling the radius of the pipe. You go from a 1-inch pipe to a 2-inch pipe. It doesn't double the flow rate. It goes up 16 times. Yeah, that's impressive. Okay, so that's why the house, your flow to your house is like a 1.5-inch pipe, and then that can supply all of the water needs of your house, and then it's neck down to these smaller pipes, inside the house.
What was the name of the equation that you said?
Poiseuille's equation.
Poiseuille's?
Yeah, Poissele. Anyway, it's at the very end of those notes. It's a really difficult word to spell for me. Yeah, that's right. Mm-hmm. Yeah. And so we've got a lot of stuff covered in the next couple of lectures, but it's all on that one homework because the exam is next Wednesday. So it's a pretty quick turnaround. So essentially this homework on Saturday is the exam. So look at that, know how to do all of those problems. Bring your questions on Monday for sure. But we do have material to cover Monday, but if you're looking ahead, then it'll be easier to get through. Okay. So how do we measure molecular velocities? Well, this is a fun little experiment. If we have this motor, this computer controlled motor, we can spin it at different speeds. We have this oven here. This is a fantastic little oven called a Knudsen cell. Let's see, cell with an S. I don't think so. Okay, and so we can have like a metal or some kind of molecular substance in here. We warm it up, and then we just have a pinhole here or a couple of skimmers. And so these particles all come out. A lot of them hit the guard. They don't get out. But the ones that go through the middle, then we have a beam. So this is a molecular beam. And you'll look in the literature, you'll see molecular beam experiments, and this is how they're set up. Then they have this huge vacuum chamber with a very low vacuum. I don't put an exclamation point on that. Because think about it. For these atoms or molecules, let's say atoms, they have to make it all the way to the detector without hitting any other gaseous molecules. And so if there's a pressure in there, then you've got pressure from the gas molecules. And so if a molecule is coming along here and it gets in the way at the wrong time, it's going to get hit. And so that's part of what we're calculating today is the probability of having collisions in a particular distance, in a particular pressure, and so on. And it's all based upon the velocities of the gases, which is based upon the temperature and also the pressure. Okay, so we have this gas going through here. Now notice there's two slits in here separated by some little angle, theta. And that is like a velocity filter. So only certain speeds can make it through both slits. So we're spinning this, if we spin this at a particular speed, then it's going to filter. The really fast ones hit here, the really slow ones hit here. Because they don't make it, the little window opens up and then they're not there yet, and so then they hit after the slit. So only certain speeds will make it through the slit. And so we detect, so like we dial in a particular speed and we're detecting the particular molecules that are at that speed. Then we just speed up the motor a little bit and we get faster molecules through. And we slow the motor down, we get slower molecules through. And so we just set at a particular speed, count how much signal we have, turn up the speed, more signal, turn up the speed, more signal, and we can just filter out and we can get this distribution. So that's where this distribution curve comes from. So we ramp up the speed of that motor and we're filtering out all of the different speeds of the gases. And like if you run two different temperatures of gases, you've got these two different ones. Like 0C is the blue curve, 100C is the red curve. And we have this distribution of velocities. So remember that even though we use that equipartition theorem for the gases, that is the average or the RMS velocity that gives us that 3/2 RT. That's the average or RMS, root mean squared velocity. That's a big distribution. You've got some particles with a lot more energy and some particles with a lot less energy, which means some have higher velocities, some have slower velocities. This is the origin, say, of vapor pressure too. So like if this is enough velocity for the gas to escape the surface of a liquid, then notice that 100 C would have more molecules that have the energy to escape the liquid, and at 0 C you have fewer molecules that have enough energy to escape the liquid. Okay. So this is all predicted by statistical thermodynamics, and in 1877 this was the curve that Boltzman was using or trying to model with his theory. And so he starts out his paper by saying, let's just, for the ease of statistics, let's just create quantized or numerical, he did it numerically, let's create particular velocities and solve the problem that way. He even said in the paper, I'm not saying that nature is like this, but for simplicity's sake, we'll just pick discrete velocities and solve the problem. And he got a rough approximation of this curve, and then he did it with analytical calculus and proved the whole smooth distribution. But that math that he introduced for quantized velocities was then used by Max Planck in quantized energies for the blackbody radiation. So that's why Planck said, I knew the answer, but I was resistant to use it because it was making a claim then about nature being quantized that he wasn't ready to make. But then it was the photoelectric effect that sort of hammered that in and said, yes, nature appears to be quantized. So this effect of temperature on a fusion rate, at higher temperatures, you have a higher diffusion rate. And so it's the square root dependence on temperature. So we know the temperatures here. Let's say this looks like 500 meters per second. So if we have at 0 C 500 meters per second, what is the speed at 100 degrees C? Okay. And so remember, you can always do these kinds of ratio problems. We don't know what gas this is, but we don't need to because we can do ones and twos. So we can do velocity 1 over velocity 2 is proportional to the square root of temperature 1 over temperature 2. Erase that line there. And so we know 3 out of the 4 variables, pretty straightforward. So now one thing I want to show you here, let's call velocity 2 our 500 meters per second. So we have u1 is equal to 500 meters per second. Okay, that is related to, and I'm going to do it wrong, okay, first, and then we'll do it right. Okay, so you're looking at the problem and you just put in all the little numbers here, and do you see a problem? You're like, oh dang, it's infinity. We raised the temperature to 100 and, velocity is at infinity. So we never ever do thermodynamic calculations in Celsius. We always do them in Kelvin. Okay, so that's 273 Kelvin and 373 Kelvin. And notice if you were to assume that it was just a proportionality, you would be wrong. You have to take into account the power that is raised to it, so you have to do that to square root dependence. So can someone do the math on this one? What's our fraction here? 373 over 273. Okay. And so then multiply that by 500.
Did you want the square root?
Yeah, take the square root. And, yeah.
1.17 is the square root.
Okay.
Yeah.
1.17 and then multiply by 500.
Then it's 584.
Okay, so it's gone up a little bit, right? And because it looks like we've raised the temperature a huge amount, going from 0 to 100, but we really haven't changed it that much. We've gone from 273 to 373. Okay. Now, effective mass is just over the square root of the mass, and so the smallest masses are going to be the highest root mean square velocity, and then as they get heavier, they sort of all converge down here. So here's the dependence on mass of the different molecules. Now remember, this root mean squared velocity here is essentially this figure of merit that's supposed to characterize the whole distribution. And so this would be the RMS values for all of these distributions. So it does, of course, have that mass dependence, but again, we've got this distribution. Now, notice how widespread the distribution is for the smaller molecules, versus the larger ones. So even though it just seems real simple to follow this root mean square velocity out, you see for the smaller molecules, you have a broader range of velocities. You've got a huge spread as it moves out. This sort of makes sense because you're going to have some molecules that are really, really slow and really cold, no matter what the temperature of the gas is. And so that it's sort of pinned to 0. So if you're going to have an average velocity or a root mean square velocity that's really high, it's got to be spread out because it's got to go down and touch 0. And so you're kind of pinned at 0, and you're just stretching that distribution out further for a light gas and then cramming it all up against 0 for a heavy gas. And so here are the other velocity moments. Again, that term moment is just like a single number to represent a distribution. And here they are shown on the curve. So the MP, that means most probable, right? So that's the highest probability. So MP is most probable. But these curves are not symmetric. If this were a Gaussian, the most probable would be the same as the average and would be the same as the root mean squared. But because these distributions are asymmetric, we have a separation in these 3 moments. So the most probable is less than the average, which is less than the root mean squared. And these have, different pieces to them. It was the RMS one that sort of matched the equipartition theorem for energy. So that's why it's used so frequently, because it matches that equipartition theorem. But the others have other factors in there, like the average has a factor of pi and 8, and then the most probable has a factor of 2. So there are some things in here that are equal, right? The RT over M. And so if you have one and want to convert the other to the other, let's make all of these, let's try to figure out how we can get a relationship between all 3 of these. And that's also in the homework. If you've given one, what is the other? Okay. So let's solve all of these, or let's put everything on the left except RT over M, okay? And so let's say the new MP over the square root of 2 is equal to the square root of RT over M. Y'all see what I did there? Pretty straightforward. And then let's take this new average over 8, the square root of 8, times the square root of pi. You see what I'm doing? That's equal to the square root of RT over M. And then this one, the root mean squared over the square root of 3 is equal to the square root of RT over M. So since all three of these pieces equal the same thing, they're all equal to each other. So if I need to get from one to the other, I have this triple relationship. I have nu MP over 2 is equal to nu av root pi over root 8. And that's equal to the nu RMS over root 3. So that's your relationship between any one of those. Yes. What did I do? Oh yeah, thank you. Very good. So that's the way, if you've got the RMS and you want to know the average velocity, because some of these equations use the average velocity, then you can quickly get to it using these relationships. Okay. Now let's talk about this fun concept called mean free path. So the mean free path is the average distance a particle travels before it collides with another particle. And it depends upon the size of the particle, the temperature of the gas, the pressure, and the volume, because that's going to tell you how many particles you have in this tube. And so how far can this particle go before it collides with another particle? And these things are all moving, but as this particle, say, moves into this cylinder, maybe this one's moving out. Okay, so it's a dynamic system. So this is all, again, on average, how far can a particle go before it collides with another particle? And its average is called the mean free path. Now, this is for two different particles, like particle 1 and particle 2. You have radius 1 and radius 2. If you have the same, it's a particle in itself. If you just have say a cylinder of oxygen, you can just calculate oxygen colliding with oxygen. But anyway, we make it for two particles, and that's what these equations are for. So how far can it go? Let's look at the equations. So here's our equations. This Z11 is particle 1 colliding with another particle 1. And it has the partial pressure of 1. And the equation is a little different than what you have in your notes. I went ahead and consolidated that piece on the right. That is the average velocity. So that little piece on the right with the square root, those pieces in there just are the average velocity. So this is the partial pressure of particle 1. Obviously, P2 is the partial pressure of particle 2. So this would be, again, the probability or the collisional frequency of particle 1 hitting particle 2. It's going to depend upon how much particle 2 you have in there. You can imagine that these are going to be important equations for like reaction rates in the gas phase too. How often does particle 1 collide with particle 2? If you want to speed up that reaction rate, just increase the partial pressure of particle 2, and you'll get more collisions. Okay. The mean free path then is that average velocity of the gas divided by these collisional frequencies. Okay. Each of those collisional frequencies has this average velocity in it, so that's going to cancel. So you end up with this equation. If we just want to talk about a pure sample of gas, particle 1 hitting itself, which is pretty simple to do, then this is the equation. The main take-home is that the pressure is in the denominator here. And then also the size of the molecule here is in the denominator. So again, if you have a smaller particle, it's harder to hit. And so your mean free path gets longer. All right, because you got a smaller target. Okay. If you've got a smaller pressure, then your path gets longer, and you can go further before you hit another particle on average. And so here's some examples. What are the mean free path and collisional frequency of argon gas at 1 atmosphere and room temperature? So we can calculate that mean free path using our pressure at 1 atmosphere. We're going to use the ideal gas constant in terms of the 0.082. Actually, we can use the pressure of 1 atmosphere definition into pascals. 101.325 pascals, which is equal to a Newton per meter squared. Okay, and so we have this joule here that's going to be a kilogram meter squared per second squared. We have Avogadro's number in here, so that gets rid of the moles. In our joule, we have the temperature in Kelvin, and pascals is a kilogram meter per second squared per meter squared. So some of those meters cancel. Okay, and then we have the cross section of the gas. And so we figure out, we can look up the radius of argon squared, so we get that cross sectional area pi r squared for argon, and that's what we end up with here. So that goes right there. So this meter squared here cancels the 1 from the pascals, and then this in the joule, the meter squared on top cancels here, and so we're left with a meter on top. We have the kilograms from pascals canceling the kilograms of the joule. Kelvin's canceled, moles canceled, everything's canceled, and we have a length. So that's the only unit that survives all of this. Okay. And so then we end up with this 80 nanometers. Not very much, if you think about it. So it only goes 80 nanometers on average before it hits another gas molecule. Okay, that's at 1 atmosphere. Okay. So let's see, what would be the collisional frequency then? So let's calculate Z11. We have to know that mean free path to calculate Z11, okay, and our average velocity, so we put in all of these terms. So we end up here with the kilogram per mole and the molar mass. The per moles cancel. The joule here is a kilogram meters squared per second squared. So the kilograms have canceled. Kelvin's canceled, okay. And then we end up with meters per squared per second squared inside the square root. So that's nice. We end up with a velocity of meters per second. The meters cancel, and so we're ending up with units of per second. So the squares are gone from the square root. The meter cancels here. So we end up with seconds to the -1. So that's, again, a frequency calculation. What's not listed is the collision part. So it's collisions per second. So our collision frequency is just a frequency. How many things happen per second. And so we end up with this 5 times 10 to the 9th per second. So 5 billion collisions per second at 1 atmosphere and room temperature. It's hard to get your mind around that on average an argon gas at 1 atmosphere, I mean that's where we're at right now, 1 atmosphere, that there's 5 billion collisions. That's atom to atom every second. Okay. Time between collisions, if you just take 1 over that, you get the sort of the period, and that's 200 picoseconds. So 10 to the minus 10 seconds of rest before it gets hit again. So it's just hard to get your mind around how many collisions we have in a given second. And this is the pressure that we experience. And so the nitrogen and oxygen's not that different. Hitting our skin, a billion times a second. That's what's keeping us together. this whole thing in Star Wars where Princess Leia gets sucked out into space and she just freezes. Okay, yeah, maybe she would freeze, but she would also just burst, you know. It'd be much more gruesome than her just kind of getting frosty and then drawing herself back into the ship with the Force. Okay, so it would not be good. Certainly her eyes and other things would be gone instantly. So, yeah, not nice to think about. Now, we can do two things. We are done with this section of notes. And the reason why you notice that the notes were posted late is because this section, I really have 5 parts and crammed into 3 lectures. Okay, and so I've combined diffusion with this in the past. This time I chose to put diffusion with thermal conductivity. So we can start the next set of notes now in the next 15 minutes, or we can just cram it onto Friday and Monday. So Friday, Monday? No, start now? Okay. Okay, so let's do that. We'll go on to the next set of notes. I realize you may not have them printed out, but it's going to be okay. We'll introduce the idea of transport. And so we'll get just through the idea of transport, and then we'll talk about the transport coefficients in particular on Friday and on Monday. Okay, y'all are fantastically inspiring. So I'm excited that you're like, wow, let's go. All right, so let's, thermal conductivity and diffusion set of notes here. I'm going to pause the video or stop the video and then start it.